Yeah, so I'm going to talk, mostly I wanted to talk about this paper, Condensation, a Theory of Concepts. Uh, I'm also going to say a bit about an earlier paper by John Wentworth and David Laurel. Uh, and so, what I'm doing broadly, I want to think about concepts. I want to think about, a model as learning some concepts about the world, as making some sort of meaningful sense of the world. And I'm going to talk about this mathematically using latent variables. Uh, and so broadly, the way that I'm going to do this, first I want to say a bit about how we should think of what machine learning models are, what they're for, what they're doing, and in particular this idea of representation learning that, we often say informally learning representations. In interpretability, we think we're looking at representations. And I'm not going to say precisely what representations are, but I think I want to say a bit about how I think about representations. And then I'm going to go into this idea condensation. There's going to be Venn diagrams, and we'll see these things. Sort of the slogan I want to use is that a representation should be useful for many things. And so so here are three examples that maybe make this sentence mean something to you. So one is pre-trained neural networks. We often talk about the loss. We have training curves, but the point of a neural network isn't really to do well on the training distribution, and it's not to do well on an out of training sample. It's to learn something about the world. And this shows up in that we can fine tune it, and in that we have in context learning where it might be able to make sense of some new sort of situation that is sort of only very indirectly analogous to things that it's seen in context. And so another sort of angle at useful for many things. This is sort of what we want out of scientific theory. Often we say that scientific theory should be unifying. We say that Newton unified terrestrial mechanics and celestial mechanics. And we can sort of contrast this to maybe theory against practice. In practice, we want to get something done. Maybe alchemy, maybe, the alchemists didn't turn lead into gold, but they could do some things, but they didn't have enough perspective on what they were doing to use that more broadly. And then also just, everyday human knowledge. If I can debug some code, we don't say, I just know how to do that, it came to me in a dream. We say, I have some knowledge about, the language, the libraries I'm using, my code base, and I'm drawing on this knowledge. And I can draw on it for many different things. And so, you can give a bit of a precise model in which something that I want to say is representation learning is happening. And this will be kind of something like pre-training, basically. But I guess it's just theoretical. I'm going to actually analyze the situation very briefly, rather than just showing you a graph of a learning curve. And so the problem, we can just think of linear regression, right? If we have a data set of pairs, so we have we use features in weird ways, but we have our given predictors. We have our big Excel sheet where we have a bunch of vectors, and then we have our labels that we're trying to predict in a linear model. So if the number of if the feature dimension is much lower than the number of data points, we just can't hope to do very well on this. There will just be directions in the vector space that we can't explore. But now we can give an alternative where we have something like unsupervised pre-training. So in this picture, what we're going to do is we're going to have our labeled data set that will be like our fine-tuning. We're also going to have an unlabeled set that's just some samples from the distribution on X. So I haven't said anything about what the distribution on the predictors X is yet. But let's say that it's well described by a sparse dictionary. So this is used in interpretability and sparse autoencoders. This is also, I mean, in neuroscience, people like this, sparse coding. But just what this means formally, it's like each of our predictor vectors, we have these dictionary vectors. So they're living in the same space as the feature vectors. And each of the feature vectors is the, well, sorry, I shouldn't use feature this way because people use it in confusing ways, in both ways. But yeah, each of the predictor vectors, like each of the input vectors, let's say, is the sum of only a few terms. So like S is much less than P. P is the dimension of the space. So right, you can think you have this big high dimensional space, but your data actually lives in like some union of low dimensional subspaces. These spaces are only S dimensional, even though the space as a whole is P dimensional. And it's, you know, there's many spaces because I could take any, you know, choosing S out of, I guess like L choose S possibilities, but that's still much less than this whole P-dimensional space. And so under certain assumptions about the distribution of the coefficients of these sparse linear combinations, and also just in practice, we find we can learn this dictionary from this sort of unsupervised set, and it's very good. I mean, the sample complexity and the runtime are polynomial, including in the log of the reconstruction error. So right, I can get twice as good reconstruct. You know, I can get, I guess, the square of the reconstruction error, so much smaller error that only doubles the log. So it's quite good. We can learn this dictionary, and then we can do a sparse linear regression, so like an L1 regression, once we know this dictionary. So this pre-training sort of helps a lot. And so this is what I want to think of as an example of what representation learning is doing. And so what's the point of this? Yeah, I mean, the first point, I mean, sort of just what I'm saying, I think we should think the point of, you know, something like an LLM, something pre-trained, is to learn representations. The point, like, why we care about it, why it's, you know, I mean, we have phenomena like hallucinations that sort of make sense from a next token perspective. This is a plausible continuation, but that's not what's useful to us. And in general, we want to get at these representations. I mean, from a safety perspective, we want to have understanding of these models. The representations, you know, we might think should be what's understandable. And also I like to tell sort of a language story that, you know, different agents can make sense of each other because they end up with similar concepts. And, you know, when we do interpretability, we see like these SAE features, they make sense to us. Well, why do they make sense to us? I mean, if we think about something like this example, it might be that Y is a sparse linear combination, but it might, and so we can predict Y, but it might be that many things you could predict better once you know what these dictionary features are. So like many different agents have reason to learn what these dictionary features are. So yeah, so now, but there's this question, what should these representations look like? And so, yeah, so I'm going to talk about how I have been thinking about that. So, yeah, so I tried to put it, I mean, I want to use maybe some sort of vaguely physics suggesting language. So, you know, we have a family of random variables. So we can think of these as living on some space. There are points, and so X is like a field configuration. And so, but yeah, so it's a joint distribution on some family of variables. And so I want to think of these variables as things that are large enough to have, you know, some informal notion of a concept present in them. I want to say, you know, maybe these variables are texts. So, you know, I could take the Wikipedia article about the Golden Gate Bridge. I could take, you know, a narrative text about, you know, set in San Francisco where the Golden Gate Bridge might appear. I could take, you know, a technical article about the construction of the Golden Gate Bridge. And I want to say these texts use this concept of the Golden Gate Bridge, whereas some other texts, you know, don't. The text, you know, the Wikipedia article about squirrels does not draw on the concept of the Golden Gate Bridge. And so So yeah, so this is sort of an informal picture that sort of makes a lot of sense to us. It's sort of kind of the picture we have when we look at things like SAE features. And so I want to say something precise about. Well, I want to have some theory about this. And yeah, so yeah, something I should maybe clarify. I'm treating texts as random variables, and then I'm talking about the Wikipedia article for the Golden Gate Bridge. I want to say like that has mutual information with another x s prime if s prime is the story set in San Francisco. And so what is the distribution? Because it's a text. It's just that text. It's just a string. It's not random. So we could make all this precise using Kolmogorov complexity, which is sort of how I would really think about it. I decided not to put in a bunch about Kolmogorov complexity, but broadly speaking, it's a way of like assigning an information content to an individual object about how complex it is. A long string of all zeros is less complex than a book. But I mean, we could also think just, maybe there's some kind of distribution that we feel like is the ways that this text could have been differently. And we can, without making that any more precise, we can use probabilistic language to talk about it. And so, yeah, so I mentioned already mutual information. So I'm going to use this sort of language of mutual information to talk about the situation. So often we can depict mutual information with a Venn diagram like this. But so what does this actually mean? It's sort of just a mnemonic for some identities. And so I've written some of the identities down here. I mean, you can derive other identities from these. But so what this means, like we can think of each segment of the Venn diagram as just a real number. So this one is the conditional entropy of y given x. This one is the mutual information of x and y. And so, taking these together, we get this circle, which is the information content of y as a whole. What y is that part of the information that it shares with x, and that part that it has on its own. But what this Venn diagram doesn't depict is random variables. So here is a different diagram that I've also drawn as a Venn diagram. But I mean, here I've sort of put variables in the segments. And this is sort of maybe what we want it to mean, but this isn't what it means, or this isn't what the previous diagram means. So it's like there's some maybe some concept that represents the shared information, the concept that is, those facts about the Golden Gate Bridge. Maybe that's what x and y have in common. And so we want there to be some random variable whose entropy is the mutual information of x and y, and such that, we have these same sort of equations. The total information in x is the information in the shared concept, plus the remaining information. The same for y. And then finally, we want x and y to be independent given lambda. This concept of the set of concepts exhausts what they share, exhausts their mutual information. And so this diagram that I haven't given a precise meaning, it suggests these equations. It would be nice if these equations held. And so this is not possible in general. It's if you give me a joint distribution on two variables, then there does not have to be, they're in general position. There is not a random variable lambda that satisfies these equations. But we want to pretend that that's the case. We want to say, that's our intuitive picture of concepts. How far is that from being true? What would be the case if that were true that is maybe true approximately in some case that we're interested in, some case where we feel that our intuitive picture of concepts does a good job of describing what's going on in terms of information. And so, we're going to try to make this true. And so, so you can also, I mean, that was two, you could have as many variables as you want, and then these diagrams sort of get very complicated. One thing that happens in particular, in the middle, I mean, this is going to be some linear combination with like some inclusion-exclusion sort of idea out of these basic things, the entropy of Z, the entropy of Y, the joint entropy of Z and Y. It's going to be this big linear combination. In general, this thing that I'm not going to talk too much about can be negative. And so if it's negative, it really doesn't make sense to say, you know, what if there is some variable with this entropy? This would be a negative number. It can't be the entropy of any variable. But yeah, so let's say what this means in terms of this sort of distribution. I mean, we can say this field theory on these x's. And so again, we might think of the x's as random variables that are these texts or these parts of the data. And so yeah, so okay, so here's what I think it should mean. So we have our field theory on x, and we're going to extend it. So now it's a joint distribution on x together with some more variables that I'm going to call these variables that we introduced latent variables. Lambda t for t in, you know, some other set t. And so I had this idea that, you know, some concepts contribute to certain texts and other concepts don't contribute to those same texts. So okay, that's just a relation. We have a subset of t cross s, and so I'm going to say that xs is actually a deterministic function of lambda t for t and s. And so I'm going to use this language determined by sometimes, but this just means, you know, there exists a deterministic function. Now, this might not fit so well our concept picture. We might say that, you know, yes, these concepts contribute some of the information, but maybe there's some residual information that doesn't feel very conceptual. Here we can put that in with extra variables. We might feel like those variables are maybe less conceptual than these, but this is just the formalism I'm going to use. I hope that we can keep that straight. Some of them sort of have this clearer conceptual interpretation, and others are just like, well, this is the formalism. There's going to be other latent variables, and yeah, I mean, you can change this, but I don't know. This is how. And so yeah, so I'm talking about this in terms of texts, but another sort of picture that we might like to have in mind is sort of the causal diagrams. I mean, if you're familiar with, this is going to be the only slide about causal diagrams, but if you're familiar with the language of causal diagrams, we might have some idea that like we have some joint distribution on some observed variables, but then we also have some latent variables. So maybe we'd like some sort of algorithm that, given this distribution, discovers this graph, discovers that you should have 3 latent variables and they should look like this. And so then we might think of the, you know, these y's as the latent variables, and so we'll say, you know, y3 contributes to x4, y3 contributes to x3, but y3 does not contribute to x1. And then y1, I mean, it's sort of, I mean, in causal graphs, we have an arrow from y1 to y2. But here, I'm not going to focus on that so much. I'm going to say y1 contributes to x1, x2, x3, which I guess is a superset. That's what's going to matter. That's a superset of who y2 contributes to. And so in general, I said we want to extend a distribution from, you know, this field with the given variables to also having these latent variables. But I mean, you know, there's many ways to do that in general. I haven't given any conditions on it yet. But, you know, if you want to know how might one do this, well, every time you have a causal graph, that's one way of doing this. That's one way of writing down a set of latent variables, such that you know, we have the, well, we don't actually have the determining relation. We need like some extra, the idiosyncratic for each one. And sometimes causal graphs are written this way, but yeah, let's move on from causal graphs. Yeah, so that's sort of my picture of how I want to think about concepts. But then, yeah, so we have a further topic, I guess, that I'm going to call objectivity. And so this is some idea that, maybe in some circumstances there's a right set of concepts to use. Maybe these concepts have some sort of validity or uniqueness, or especially approximate uniqueness. And so so there are some theorems about this. And so first I'll do the Wentworth and Laurel theorems, and then this isn't really going to use all the we'll see the different theorems, but this I guess is some initial version, and then we'll modify this. And so in particular, the difference here, we're going to have a single latent variable, lambda, rather than, I had all this lambda t for some auxiliary sets t. But this is going to give some first idea of what I might mean by objectivity. So so Wentworth and Laurel, they define these. I don't really use these words. I don't know. Maybe they'd be intuitive if I use them more. But we'll define them. So we say that lambda mediates between this joint distribution, this set x of s, if the x values are jointly conditionally independent, sort of conditional on lambda. So, right, I mean, you can think of like, you have a coin with an unknown bias. You flip the coin many times. There's a correlation, there's a probabilistic dependence between the different flips of the coin, because each flip of the coin gives you information about the bias, which then tells you what the other flip is likely to be. But conditionally on the bias, then these flips of the coin become independent. And then we can also say that lambda is a redund for, I
was just going to ask, does it make sense to consider the case where S is a set with one element? Is that a valid example? I feel like in that case, the first condition is vacuous. Like,
yes. And
then I don't understand how the theorem applies there. That would say you could take any lambda. You could take lambda prime to be any statistic in X of the single elements.
Oh, this is backwards. Yeah, it's lambda. I think this is backwards. I think lambda prime is supposed to determine lambda.
That sounds.
Mediator determines redund for sure.
Mediator. Oh, okay. Yeah, let's see. Mediator.
Actually, I don't think it applies when.
Yeah, I mean it should apply when. Oh, maybe it doesn't. Yeah, maybe.
There's just one random variable, like one observable.
Yeah, because maybe they like do something that involves non-emptiness.
Yeah, I think so.
Or like involves like picking two different things.
Yeah, for sure.
Yeah, because there's
In the proof, you have to have at least two.
Yes, have at least two. Okay.
Yeah. Okay. Yeah. Maybe I took this too direct. I mean, I sort of translated it into my own language. Maybe I took this too directly without thinking it through. So I guess let's see if that makes sense. So so the mediator, they're jointly conditionally independent, and then the redund. So this is the latent variable lambda is determined by each individual, the field value at some point. So one flip of a biased coin doesn't determine the bias of the coin, but maybe we think of each x as many flips of the coin. But we have many, I guess, groups of flips. And then many flips of the coin don't determine the bias of the coin either. But this theorem is going to be also true in some approximate form. So many flips of the coin approximately determine the bias of the coin. And so there, I mean, so as we said, if one variable mediates and one is a redund, the first determines the second. What one sort of thing that makes this compelling is taking both of the latent variables to have both properties. So we'll say that a variable is a natural latent if it both mediates and is a redund. And so if we have two, so in this coin example, we want to say that the bias of the coin is approximately the only natural latent. So yes, the bias of the coin, it both mediates, the flips of the coin are conditionally independent given the bias, and also, sorry, I guess the chunks of many flips of the coin are conditionally independent given the bias. And the bias is also approximately determined. So its conditional entropy given the given a chunk of flips is small. So any other latent variable that that satisfies those two properties is going to both approximately determine. Yeah, let's go to the next slide because that's the oh, I guess, yeah, I wrote it as a big inequality. Yeah, let's look at this slide. Yeah, so it's going to both approximately determine and approximately be determined by the other. So if I have yeah, I mean, I can't give an example because there isn't another example than the bias of the coin, I suppose. And so, yeah, I mean, if you want to see I mean, yeah, they don't write this in this form in the paper. They have some like graphical language, but this is basically the approximate form of the theorem. I mean, this is just a bunch of symbols, so let's break it down a bit. I mean, these two we should think of as going together. This is the sum of the, so it's like we're conditioning on lambda. We're conditioning on the natural latent, or I guess the mediator in the one-directional form, which this is. Then we want to say, so this is the sum of now the marginal distributions, the entropies of the marginal distributions of the different point values. And then, whereas this is the joint entropy, so the whole field X, what's the entropy of that? So the sum of the marginal entropies is always at least as great as the joint entropy, and the difference between these is a kind of mutual information, a kind of multivariate mutual information. So this term, these two taken together, sort of measures how far we are from approximate, how far we are from conditional independence. We can also think of this as the KL divergence. This is like the expected KL divergence between the joint distribution and the product of the marginals. And then this term, it's like how close is the field value at any one point to determining lambda prime, to determining the redund. So this is approximate determination. And so yeah, so then so what I do basically in the paper, condensation, the point is to, I mean, it's a similar sort of objectivity idea, but applied sort of to the story we were telling before of not one latent variable, many different latent variables that each are some sort of concept. You know, maybe the concept of the Golden Gate Bridge, or we can think of all the SAE features, or this sort of thing. And so, yeah, so we have a lot of text. So let's go through the elements of this theorem. So we again have the setting x of s for, so we have this field. We can think of these different texts that we're interpreting as random variables. And then before I was using these contribution relations, here I'm going to replace the contribution relations by, I'm just gonna, my set T, my set of points at which the sort of the latent field exists, is going to be, I'm just going to identify it with the set of which points in the original space it contributes to. So the contribution relation is going to be the elementhood relation between the point and the set. So I feel like I said that sort of strangely, but maybe that makes sense. Yeah, I mean, I guess no one's asked about it. So yeah, so now we're going to have two different latent variable models. So we can extend this marginal on the original field x to a joint on x and lambda or on x and pi. And so, yeah, so lambda, we have the set A of these additional points that are going to be the concepts, and pi, we have the, yeah, so set B of these points. And so we're going to make a number of assumptions that are sort of going to relate to the what do they call the mediation and redundancy that Wentworth and Laurel have. So the first assumption is just going to be, yeah, the cardinality of B is small. So I don't have, because a priori, I index these by the power set. You might expect some sort of exponentially sized set of new points. But yeah, I mean, the sort of errors that come from that would add up very quickly if you think about the inequality. So I want to say that that's small. Yeah. So the structure of this theorem, there's an inequality like the one on the last slide, but I'm going to use the sort of informal language of saying that things are small before showing you one form of the inequality. But
Pi is like lambda prime.
yeah, I decided not to use a prime, but yeah, pi is just like a square lambda. Yeah, so it's like, yeah. And so then I'm going to have this property that I call reconstruction. So this is sort of the equivalent of the redundancy of Wentworth and Laurel. So yeah, so it's like for each of the new lambda latents, the latents of the first model, I want to say that this new latent is approximately determined by the set of those points it contributes to. Yeah. So instead of looking at just one of the instead of this quantifier looking at just one of the things it contributes to, I'm now talking about this sort of, is it determined jointly by all the things it contributes to? And then, yeah, so this again, I mean, we can think this is an approximate form of this being a deterministic function of this. And so then the third one, that I mean, I call this the Markov condition, where I call anything that's a statement of conditional independence the Markov condition. I don't know if that's how people are used to thinking of a Markov condition. But here I did a simpler version. So there's no conditional independence. This is just independence. So now the latent variables of the second model are going to be jointly independent. And so that's somehow going to correspond to like the mediation. But now we're not stating it in terms of the latent variables of the original model. We're stating in terms of the latent variables. Or sorry, we're not stating in terms of the variables of the original model, the original field. We're stating it only of the latent variables. But it works out very similarly. So we have these two sort of models. One of them is like well reconstructed. We can figure out, given sort of the joint distribution, given that I know what the relations between all the variables are, if I observed the given field values, the x's, I could see lambda, and the other has this Markov condition that they're independent. And so then we say that lambda is approximately determined by pi. And so in particular, it's going to be, so all the B containing A. So it's like, I mean, we might think this is relatively few things, but it's like, if you want to know what lambda thinks of this sort of A concept, you have to know, or at least it's sufficient to know, what pi thinks of all the concepts that are sort of bigger than A, all the concepts that contribute to everyone A contributes to and possibly contribute to more. So we can think back to this, right? the latent for y1 contributes to everyone the latent for y2 contributes to, and also more. So yeah, so it's more complicated a statement, but the point is to be again this sort of objectivity theorem, but now for this sort of conceptual information organization. So we can think of this as a kind of isomorphism or equivalence or proximate equivalence between the latent model lambda and the latent model pi. Yeah, so that's, I went through all this text and I don't have too many more slides left, so maybe I'll pause briefly if someone wants to ask about how this works.
Think about this recursively. You have different levels of latence on a tree.
Yeah, I'm interested in that because we do have this intuitive picture that like we or like emergence or abstraction happens sort of in stages. But yeah, I mean that doesn't seem to be how this naturally works in this formalism, but it would sort of be nice to see how that might be fit into here. What yeah, so I don't have something very definite to say, I think, but yeah, I mean in a way this sort of wants to do everything at once because it's like these are maybe pretty strong conditions on what the latents have to be. It's like they want to know about all the mutual information. It's like wherever there's like a connection to be made, a unification to be made, somehow they already know about it in order to have this sort of joint independence. Yeah, so yeah, it'd be nice to like think about getting there in stages, and maybe that could be like the process of learning.
So wait, so when you say that the latents are joint independent, is that like that's pretty strong, right? That in fact means that you only have depth 1 in the tree, or am I?
So I'm gonna is the next slide a good way to no, because I just read Markov condition. Well, let's leave the slide up. Yeah, basically, jointly independent is stronger than I actually need. What I need is certain conditional independencies that will sort of be the ones you expect from kind of the tree picture. It's like children should be independent given their ancestors.
You're not a graph, like directionally.
No, it can be a graph. It's just like it's the you have this power set, and so the order is like the subset relation. So you have like the power set from like the contribution, and so it's just like you can think of that as a causal network, as an arbitrary graph you can fit into this.
So the statement of the shape for any causal
network. Yeah, like any causal. Yeah. The example I did was a tree because it's easy to draw in 2 dimensions, but you can do this translation of any causal network into a latent like, variable model in my sense.
The latents aren't dependent.
Yeah, but the latents will have the conditional independence, the Markov condition that I want.
Oh.
And so, yeah.
For the cardinality one, I know you're saying that small is a placeholder, but I'm curious, is small relative to or why?
Yeah, so that's what this slide will tell you. So maybe we'll but yeah, so it's basically because this sort of error term, this like how well do the latents of one model capture the latents of the other model? It's going to be a sum over B. So sort of the bigger B is, the more this right-hand side is adding up more and more. And then it doesn't meaningfully constrain the left-hand side as it gets too big. So that's, yeah, so what small really means is this inequality.
So the equation would still be true if B was big, but it's like not useful.
This inequality is true in general. It's true under the hypotheses. And so small is a way of talking informally about an inequality. If the right-hand side is small, then the left-hand side is small.
And this depends on some cardinality.
Yeah, because it's the sum over, we have the sum over all elements of B that are not supersets of A, so the ones that don't appear on this side. So, I mean, we can just think that's bounded by the total cardinality of B.
Is every term is smaller than 1?
No, not because every term. just the number of terms is bounded by the cardinality of B, and then you separately ask about the size of the terms. But so yeah, so it's like if you have a sum of few terms, each of which is small, then the sum is small. But
Like,
what exactly is the bound is this
should I
inequality.
think of this like in a setting like normalization as like, you know, the right hand side is like a polynomial, like much smaller than like there's some asymptotic sense in which it's small.
There's some asymptotic sense in which it's small. I don't know. I mean, like, because you could write down some latent variable model in which there's a lot of latent variables, and then this like becomes weak. Yeah, I mean, if you think of, I don't know, like, yeah, it's like an interesting family. Probably the number of latent variables will grow slowly. You know, will grow only polynomially or something like that, as the number of the ground variables x grows.
Yeah, so I'd say it's like given a log times the number of variables x. That's like standard normalization. But then what is the saying? Like, I guess like how strong is like, is this going to give me some very strong restriction? I guess I don't really have a sense, but right, the right hand side you're saying is like bounded by like something like I should think of as something proportional cardinality, but like
Yeah, well, yeah. So let's think about what this actually is. This is like the reconstruction term. What's the entropy of one of these latent variables given? It's like all the variables that B does not contribute to. So if B itself is small, yeah, you have to think also of like the sizes of these sets B, and not just how many of them there are, because that's sort of really the renormalization picture. It's like at a coarse scale we have few variables that matter, and then at the finer scale we have more variables that matter. And I have these latent variables all the way down to fully determine X, but we want to say that like if we're asking about a B, that yeah, it's like yeah, because here we have it's like all those B's that contain A. So it's like if A is reasonably big, then the B's that contain A will also be reasonably big. So we have like more objectivity at the sort of coarser scale of like the latent variables that contribute to a lot of the points, and then we have like less objectivity as we look at the latents that contribute to fewer of the points, because then like yeah, it's like when A is smaller, we now have more of these B's, and then and also like the B's that we have, yeah, it's like there's more of them and they're smaller, so it's like yeah, so like yeah, so like this term will grow when B gets smaller, and then like the sum will grow when there's more B's. But yeah, but like we want to feel like at this sort of core scale, there should be like I don't know, maybe I don't know exactly what the sort of growing logarithmically you have in mind, but that's sort of what might happen at the core scale.
A binary tree.
Yeah, yeah, like something like a binary tree. It's like the number that are left at the big scale is small. I mean, I guess it's like
And like how much? Yeah, how much is this saying? Like what's
yeah, how much is I don't know. I mean, yeah, I mean, we'd have to do an actual example, I think. But yeah, I think in these sort of simple cases, like a binary tree, it should be good as long as we have the reconstruction. Because like if the tree only has two children, that might not be good enough to reconstruct. Actually, there's a more general form of this inequality where you might be able to think about that.
Something that you need to think about ahead of time, or is this something that you can like empirically measure? Like if you have some structured data set, and then you can kind of see the relationship between A and B. Like, do you need to have this information in order to make the theory work?
Yeah, I mean, like, well, so this stuff is stated in terms of like a distribution, so it's hard to think like, if I want to think about applying it to data, I would sort of think like maybe let's like estimate the complexity of something by like asking how hard it is to learn, And so then you might sort of get these terms by looking how hard is something to learn. That's like its complexity. And yeah, but I think, yeah, I mean, I'm interested in going that more in that direction, but I don't have such definite things to say. And it's more like, now that I know these things, we could think about how to apply them. Yeah. Yeah, I guess let's do this slide because this is sort of just summing up. So so just to repeat the main sort of ideas. Yeah, I think we should be interested in representations. I think representations should be useful for many things, and this is really what we're doing with LLMs. But also, we should understand this for safety reasons. We should this is what we should be interested in sort of scientific curiosity about models. And then we have this idea of concepts that sort of reducing our understanding to some basic elements that sort of combine in this sort of set theoretic operations that just put all these concepts together. And so let's try to make this work with entropy, even though it doesn't necessarily work exactly with entropy. And then when we do this, under the right conditions, the basic elements we can say are objective. Objective is in the sense of these theorems. And so, I don't know, I took questions for a while, so I don't know if there's more questions, and maybe we want to move on. But yeah, thank you.